Hello everyone, welcome back to the channel. Today I am very excited to present the beginning of another new series which I'm hoping will last a very long time, and that's one where I get to learn a little bit more and actually read through some deep depths of technical papers. Now I don't expect this one to be easy. I'm still hoping to provide you guys with some utility through it, and I'm hoping that this still manages to get some views. Obviously I gave myself a haircut to make sure that I look good for episode number 1. And you guys were all very positive about this. I appreciate the good feedback that you gave me in my previous video, and in addition to you guys being pretty positive about it, so am I. And not only am I positive about this series, but I'm also positive with regards to my most recent STD transmission test. So without further ado, let's go ahead and get into the series, and we can go ahead and get started. Cool, so today we are going to be talking about the Amazon Dynamo paper. So to give a little bit of context, the Dynamo paper was published in 2007, although it seems like they actually rolled out Dynamo internally a couple years earlier. And I think one of the main things that I want to get across here early on in the video is that, we've already covered a lot of this stuff on the channel, right? This is basically the main driving force behind what is now Cassandra. So Cassandra is basically an open source implementation of what's described in Dynamo, and as a result, a lot of the fundamental principles of this paper we've already covered. That being said, what I think is the main benefit for me personally, having now read this paper, is the why of things, right? We understand how Cassandra works, but it becomes a question of, well, why was this necessary in the first place? What benefit did it provide over Amazon's existing database setup, and what did it accomplish to have them roll this out? So I'm really going to try and put in some extra effort to focus on that, and hopefully it gets us all some value. Now another thing is this is a pretty dense paper. If you read it yourself, it's only 16 pages, but I can say with certainty it took me maybe over 2 hours to go through, fully take notes on, and then even then I had to go back once or twice to make sure that I fully understood stuff. So I'm going to do my best to try and cover it in a relatively short period of time, and of course provide visual examples, because otherwise if I can't provide any utility or marginal value over you just reading the paper, well then maybe there's not so much of a point of me making these videos and I could just take notes on them myself. You guys can tell me that after the fact, but for now let's go ahead and talk about Dynamo. So like I mentioned, big influence behind Cassandra and ScyllaDB. I believe ScyllaDB is just like a C++ implementation of Cassandra. And then in addition, to be clear, I am not sure, it's possible this is the case, but I am not sure if this is the same implementation of current DynamoDB. Not only has it obviously been like 17 years, but additionally they could have just changed this thing as much as they want because it's not open source and I would have no way of knowing. So please don't quote me on the fact that this is the DynamoDB implementation, because I've heard that it is not. So let's go ahead and first set the scene, talk about a little bit of background, and talk about Amazon's setup at the time. So this is the early 2000s. They're a fairly new site at this point, but they're already getting big. So already at their peak usage, they have tens of millions of customers. Now I'm sure that's in the hundreds of millions, but it's still a lot. Additionally, even at this point, they have tens of thousands of servers, and they're still using a bunch of microservices. So I interned at Amazon myself. Pretty much everything is a Java microservice. Every team is just dealing with their own repo, and then you have some centralized repo finder, but the gist is that everything's running on commodity hardware, and we've got all of these small services. Because of the fact that they have so many servers, there are going to be tons of individual node failures. It's always possible that hard drives fail. They have a pretty high rate of working, but when you have this many servers, it's going to happen on a daily basis. And even more than that, what would be more catastrophic is a data center failure, in which that's going to take out multiple servers at once. So what Amazon actually looks to do here is prioritize availability. They want it to be the case that they can build some sort of data store where you can always read from it and you can always write from it. Now, of course, if you guys have heard of the CAP theorem, which we've covered on this channel plenty, it basically says that, out of consistency, availability, and, like the ability to withstand network partitions, you have to pick 2 out of 3. Now, even though this is kind of a bogus thing, the gist is, if we want to pick availability, right, we always want to be able to read, we always want to be able to write. What do we have to give up to achieve that? So the gist is whatever we do build has to be very scalable because our site is growing fast. So moving on, I think basically the main gist behind this paper and the motivator behind it in the first place is Amazon's gripes with SQL, or at least how SQL databases were working at the time. Obviously there's been some development since where these database systems are actually starting to converge a little bit, but hopefully this paints a picture of what was going on at the time, because the motivation is what's really most important here. So basically, for starters, SQL is a full managed database, right? RDBMS. So it actually requires more expensive hardware to be able to execute these joins, and also you need database administrators, so you need employees to manage it. Additionally, it doesn't really work that well for them at scale. The reason being, at least at the time, pretty much all SQL replication technologies were limited to single leader. So what they say explicitly is they choose consistency over availability. And so what that means in reality is we have some sort of semi-synchronous single leader replication. So to draw that out for you, we've got some client, the client's writing to the database. This needs to succeed. Maybe this guy over here can be written asynchronously, but at least one other write to one other node must succeed first. And what that means is that if this guy goes down, all of a sudden we can't write. So we don't have a very available system, right? Because of this need for synchronous replication to ensure the durability of our writes, all of a sudden we're in trouble. Data center failures and node failures are going to give us a really hard time. Another thing they say is that it's not too easy to use smart partitioning schemes for load balancing, and we'll see what that means in a little bit more. Cool. So what is Amazon's actual use case, right? Because they do still use SQL plenty. If you work there, or if you've just used AWS, there are many, many SQL options. However, maybe SQL is not always going to be the best choice for a given job. So the case that Amazon is actually trying to optimize for here, which is very important, is basically data stores where you only need primary key access. No fancy queries, no joins, nothing like that. Basically, all queries are going to be local to a single node. You don't need transactions or anything. You don't need ACID transactions specifically. You're probably just going to be editing and reading one row at a time. So maybe you need some row level locking, but you certainly don't need like isolation if you're editing multiple rows. So what are some examples of this? Well, Amazon shopping cart, their user preferences, their user sessions, and their product catalog are all examples of where you're probably just modifying one element at a time and you're reading one element back at a time. So again, these aren't super big files, right? This isn't like a full-on object store. These are small blobs. Cool. So again, like I mentioned, the relational model is overkill here. We don't need all of that. We certainly don't need ACID. We don't have to be grabbing all of these locks on all of these transactions. And so like I mentioned, SQL is not going to be tolerant enough of failures. At least in the prior case, using that kind of single leader replication or the semi-synchronous single leader replication, a node goes down, we're in a lot of trouble. And we always want to be able to accept writes, and similarly, we always want to be able to provide data for reads. Now again, this may compromise our data integrity a little bit, but we're going to speak about that plenty. Another thing I want to touch upon is performance measuring at Amazon. On this channel in particular, I've spent about zero time talking about how latencies are actually measured and a good way to do it. Part of which is just because I don't really know that well. So I think it's important to kind of reiterate what they mention in the paper about their SLAs. So SLAs are service level agreements, which is basically saying if I build a database, here is a guarantee about performance that you're going to get. So Amazon says basically what we like to do is provide SLAs for the 99th percentile or the 99.9th percentile slowest request. The reason being they find that ensuring anything more than that takes way too much engineering effort and doesn't make their customers that much happy. It's just diminishing returns. So again, they're looking to basically get statistics at this 99.9th slowest request. And of course, if that's the case, you want a highly available service because, maybe 0.2% of the time you can't write to SQL. Now all of a sudden, 0.1% of your requests in that 99.9th percentile that you really care about are going to take forever, and that's going to be a very, very big problem. So availability is extremely important to us at Amazon. Cool. Another thing they mention is that each Amazon page load, which I found was an interesting statistics, hits 150 different services. And this was at the time. I can only imagine how many it is now. But the gist is, if not everything conforms to its service level agreement, you're performing this massive scatter and gather query every single time. If even one person goes out of line, you're basically limited to the slowest straggler, and that's going to be a problem. So they say that the database is often the main source of latency there, so obviously we want to be sure that we're following our SLA. Okay, the next piece of this are some design principles that Amazon wants to follow when building Dynamo. I think just in general, this is not something I think about too greatly when I'm building software because I'm not building distributed databases most of the time at my job. In fact, I don't think I'm building them ever. So it's interesting to kind of see these principles at play and then how they ultimately iterate on those in their design of Dynamo. So number one is what they call incremental scalability. So what this really means is that you just want to be able to change your cluster size very quickly. And not necessarily quickly, but easily, right? Like it gets done for you and you just have to press a button. Number two is symmetry. I think this is probably the most important thing that they implement in Dynamo, which makes it very, very cool. And that is basically that every single node does the same thing. We keep everything decentralized. If you think of something like the Hadoop design, we have a name node, right? We have this single point of failure that stores all of our metadata. Dynamo doesn't have that. It's completely decentralized. And there are obviously going to be a lot of challenges that come along with taking this sort of approach. But ultimately, it's actually a very cool system because it basically means that you can go kill a node and things are going to proceed as normal. The last piece of things is going to be heterogeneity, if I'm pronouncing that correctly. I think I am. But the gist is, it's commodity hardware, but not all servers are equal. It's possible that one server gets upgraded to a newer CPU. If a server is more powerful than another, hopefully it should be doing a little bit more work. So we want to be doing work proportional to our hardware capabilities. Okay, so now I'm going to give a very high-level Dynamo overview, and this should already be familiar to a lot of you. To be clear, I'm not going to go into a super deep dive of a bunch of these topics because of the fact that I've already done so on my channel. I would hope that you're already a little bit familiar with Cassandra, and while I will go into a shallow dive of some of these things, I wouldn't expect to figure out every single semantic. You would want to watch these videos consistently. So number one is that we're using consistent hashing to split up our key range. The reason we use consistent hashing is because as opposed to just something like a hash mod n, it's basically going to allow us to add or remove nodes and more evenly balance out the sending of keys, right? It's not just like everything gets rebalanced, but rather a minimum number of keys gets shifted from their existing node to the new node. Another thing that we're going to do is use something called a gossip protocol to tell everyone what lives where, right? So all the nodes need to know which keys live on which nodes, and so they basically do that by randomly picking a node every couple of seconds and saying, hey, this is what I think the state of the world is, and then that node will do the same thing, and then that node will do the same thing, until this state of the world eventually converges on every single node in the cluster. Another thing that we do is read repair and anti-entropy. So the reason that we do this is for replica synchronization. We'll cover what that means in a little bit. And then finally, we also use quorums for data consistency. Again, we'll cover what this means in a little bit. So just as a quick refresher on consistent hashing, I basically already said it, but if you're thinking about how to hash a bunch of keys over a bunch of nodes and split them up evenly, your initial thought might be, okay, let's take a hash of a key and then do mod n, where n is the number of nodes. However, the problem is, let's say that we go ahead and add a node, hash of the key plus or mod n plus 1 is a completely different number, and all of a sudden now we're rebalancing all these keys. That's super expensive. So the gist is basically consistent hashing takes all of our keys, it takes the hash of them and puts them on this ring right here. And the ring represents the range of all the keys in their hashed form. So for example, if I want to figure out which node a key lives on, I take the hash of it, I map it out on the ring, it's right here, and then I walk the ring clockwise until I find the label for a node. You can see now that key Jordan lives on node 3. And so basically we take these things called tokens for every single node, we place them randomly on the ring, and that allows us to split up our key set. So the nice thing is that you might say, oh, well, if we just have one token per node, we're going to have a pretty skewed distribution. But if you have multiple or even randomly placed tokens per node, this more so evens out the key distribution. So the nice thing is that, let's say I go ahead and add node 4 right over here. The only keys that are actually moving that now belong on node 4 are these over here. So node 1 will send node 4, node 2 will send node 4 those keys, and then nothing else actually has to get rebalanced. Now in practice, it's a little bit more complicated than this. We're going to get to that in a little bit. Let's quickly do a refresher on quorums as well, because this is also super relevant for our Dynamo paper. So basically, we want to ensure that we have fault tolerance, right? And the way that we do that throughout all of our systems design problems, and in reality as well, is via replication. So Dynamo is using something called leaderless replication, right? So basically, a key belongs on n replicas. So those n replicas are what's called the preference list. So do remember that term because I'm going to use it a lot throughout this video. And the gist is that basically we can go ahead and read and write this key from any of the nodes in the preference list. So what is a quorum? Well, basically it's saying, okay, let's imagine that these 3 nodes make up our preference list for a given key. So n is equal to 3. Then what we can do in Dynamo is set 2 parameters, w and r. So in this case, w is basically how many nodes that we have to write to for a client to see that their write was successful. So in this case, let's say that we want to write x equals 5. Once we get positive responses from 2 nodes, we could get it from a third, but we only need it from 2, that our write was successful, the client can say, okay, my write was good, I can proceed as normal. Then we also have this parameter r. What r is saying is this is the number of nodes that you need to read from to ensure that you see a proper value, right? So it's saying, like if I'm only able to read from 1 node, my Dynamo client local to my server would be like, hey, you didn't have a successful read. However, if I can get responses from 2 nodes, the read is considered successful. So why is this useful? Well, I know that if I'm able to successfully write to 2 nodes, and I'm able to successfully read from 2 nodes, the actual most recent value that I picked is always going to be on one of the nodes that I read from, and as a result, I'll always see that write. So you don't have to worry about consistency issues as long as you're achieving quorums. So the actual equation here that we really care about is w plus r is greater than n. Cool. So another thing to note is that, this is basically going to allow us for readers to always see the most up-to-date value of a key. So to basically add to this a little bit, because I'm sure you guys have a few more questions, we're going to get to that in a second. Basically, the thing with these quorums that make them so useful in Dynamo is that they're very tunable. It means that different microservices in Amazon can configure their Dynamo in different ways, right? So again, we have to be able to pick the size of the preference list, which is n, so how many replicas each key belongs on. Basically, if that number is super high, our key is very durable. It's very unlikely that we're going to lose it to node failures. If it's super low, now all of a sudden we have a very low barrier for successful reads and writes. And the reason this is useful is because basically when you're reading and writing in DynamoDB, you're always going to be limited by the slowest node that you have to read to and write from, or rather write to and read from. But those are called stragglers, right? So if I'm writing to 2 places and one of them responds really quickly and the other takes a while to respond, but I need to be able to succeed for 2 writes, that's going to limit my speed. So, being able to have a low barrier for both of these things is going to speed up how much we can read and write at the cost of being less durable. Additionally, we can also tune our W and R values, where basically if our W is super high, it takes a lot of work for us to write because now we have to write to a bunch of places. But at the same time, then we only need to read from 1 place. So that's the example where R is 1 and W equals N. But basically, if W is higher, we've uploaded more work to the write path. If R is higher, we've uploaded more work to the read path. I guess uploaded's not the good word, but we've assigned more work to the read path. Cool. So like I mentioned, consistent hashing and quorums, as far as this is concerned, basically we need to now pick out which are the nodes in our preference list. And the way that we would do that is, let's say I hash my key, it puts me over here on the ring, and we've tuned our DynamoDB such that the size of the preference list is 3. Now this key basically belongs on this node because it's the first unique one to clockwise of it. And then we take the next unique node clockwise, and then we take the next unique node going clockwise, and we've made up our preference list. So we would know that for this particular key, it should live on both node 1, node 2, and node 3. And since every single Dynamo node is, has this ring locally and caches the values on it, it should know that, if it's coordinating a read or write request, exactly where to read from and write to. So yeah, the gist is we just go clockwise until we find those distinct nodes. Cool. Now the one thing that should have been up in the air to you at this point, because I didn't cover it just yet, is, like I mentioned, it's very possible that you can have a quorum and you can read 2 different values from 2 different nodes, right? So here's an example of that. Let's say I'm a writer and I am going to write x equals 8 at timestamp 200. And that hits 2 of my nodes, so it's a successful write. And then we have a reader, and the reader is going to read x equals 8 from this node down here, and it's also going to read x equals 7 from this node over here. So which one is the actual proper value, because those two nodes disagree on it? Well, the reader can use the actual write timestamps themselves to differentiate and figure out which one is better, which is known as last write wins. So the nice thing about it is to actually store a timestamp per key is constant space, which is very nice. And additionally, another thing about it is if I'm a writer, I can basically just go ahead and write to the node, and the node itself can assign a timestamp. There doesn't have to be any coordination like we'll see in a little bit with version vectors. At the same time, timestamps are, first of all, they're not precise because all of these servers can have clock drift relative to one another. And secondly, if we were to have two concurrent writes at the same time, last write wins is not able to detect them. So that is going to be a little bit of a problem as well, depending on your use case. So let's talk about write versioning now with version vectors. So the gist is, if you guys recall, a version vector basically works like the following. It basically keeps track of, for every single node in our preference list, how many writes that node has handled. So in this case, it's basically saying node 1 has handled 0 writes for this key. And then it's saying node 2 has handled 1 write for the key, and then this is saying node 3 has handled 0 writes for the key. So let's imagine that we have a writer over here. And we can already see that all three of the replicas start out completely synced up with one another. And they agree that basically the middle node has had 1 write for the key. Okay, so we have some writer, and what it's got to do is basically hit one of the replicas to initiate the write as what we will call the coordinator. Now the reason we need to have this done through a coordinator is because we need to actually increment our version vector. And the only way we can increment our version vector is if it goes through one of these 3 nodes. So it goes to the coordinator, this is node 3. Node 3 then goes ahead and say, okay, we're going to increment this guy right here because I'm handling the write. The coordinator then successfully writes to this node over here on the left, so it also increments its version vector for node 3, and then let's say that the write actually fails over to the middle node, and so this guy stays as a 0 instead of a 1. Now what happens when the reader actually reads from this node over here and this node over here is that it can look at the 2 version vectors. Because all of the elements in this version vector are greater than or equal to all of the elements in this version vector, we know that this one must have come after this guy over here, and as a result we know that x equals 9 is the proper value. On the other hand, if you have 2 version vectors where their numbers are kind of interleaved, right? One of the version vectors has elements that are greater than the other version vector and then also has elements that are less than the other version vector in the same indices, then those writes would be considered concurrent. So it would be very great if we always used the same node as the coordinator, right? Because then we would have a total ordering of our writes. That's not really feasible because the whole point is we want high availability, and if we're always using the same node, we don't really have high availability because then that node goes down and we can't accept any writes anymore. And also the load is just not evenly distributed over all of our nodes in the cluster, which thus takes away the idea of symmetry. So that's bad. We basically want to let any of the nodes in the preference list coordinate a write. So what are the pros of this approach? Well, for starters, we can detect concurrent writes, which is really great. On the flip side, we do have linear space complexity for each version vector compared to the size of the preference list. Now in practice, this probably isn't that big because it's not like you want to choose a preference list that's like 99 replicas. You probably want to choose one that's 3 or 5. But it is still bigger than your timestamp, and that's not insignificant. Like I mentioned as well, just to get the new version vector, your write has to be coordinated by the member of the preference list. This is contrary to the timestamp where, because it doesn't have to go through any particular node because you're just assigning a timestamp at the server that receives it, you can basically just do a client timestamp right here from the client, and then the server will use that client timestamp. Or the servers can assign it themselves, but then the timestamp would be different across servers. So ideally you probably just have the client assign it and then the servers apply it. It doesn't have to go through one coordinator. Cool, hopefully that makes sense so far. So the next piece is actually choosing the coordinator. So like I mentioned, in Dynamo, when you're making a write and you're using version vectors, your write has to be coordinated by one of the nodes in the preference list. So I guess the question is, well, which one do we actually choose? For starters, every single node, recall, because of our gossip protocol, knows all the membership information, where the membership information is what nodes exist and which keys belong on which nodes. Additionally, in theory, as an optimization, you could actually have clients also listening to the gossip protocol. Because then, for certain writes where you're using last write wins and you don't actually need to use a Dynamo node as the coordinator, you could just have the client do it itself and it saves you a network hop. Similarly, for reads, you also don't really need to have a node in the preference list coordinating that read, and so you could do it directly from the client if the client is subscribing to the gossip, or you could just do it from any node in the Dynamo cluster. But like I mentioned, the fundamental thing here is just version vector writes have to be coordinated by a node in their preference list. So basically, if you're writing for a given key, that write needs to be coordinated by one of its replicas. Doesn't matter which, but it's got to be coordinated by one of its replicas. And there might be a lot more nodes than there are replicas for that key, right? We might set our preference list size to 3, but there might be 100 total nodes in our Dynamo cluster. That's totally fine. So another thing that they do in Dynamo as an optimization is they note that typically when we're writing a key, it's after we've read the previous value. So the nice thing about that is when we read the previous value, we're reading it from one of the replicas. And so we can actually figure out which replica responded fastest to us, and not only which one responded fastest, but which one responded fastest with up-to-date data. And then because of that, we can actually go ahead and use the coordinate, or basically select our coordinator as the replica that responded the fastest with up-to-date data. The reason being we want to use the one with up-to-date data because then we're less likely to have a version vector conflict or concurrent writes. Okay, let's move on to read repair. I've discussed this plenty in my channel, but let's go ahead and do a quick overview of it. So basically, when you're doing a read, right, you have this concept of a read coordinator. That could be a node in Dynamo. It could be the client if the client is subscribing to the gossip protocol. So basically, the read coordinator knows a couple of things because we have quorums. We have, one, the most up-to-date data because quorum should get us consistent data. And number two, we also know which nodes are giving us back stale data because we're getting responses from multiple nodes and we're seeing all of them. So actually, the coordinator can then just go ahead and say, ooh, wait a second, you gave me back stale data, let me go ahead and get you the up-to-date data. You just responded to me, so I can probably communicate with you, so this is most likely going to work. It doesn't always. It's possible that we have a network failure between us when I try and write there. However, at the same time, it's pretty unlikely, and if it does happen, that's why we have things like anti-entropy, which we'll discuss in a little bit. So what does this actually look like? Let's say our read coordinator is a client. Basically, I read from these two nodes over here. One sees that x is 10 at timestamp 1. The other says that x is 11 at timestamp equals 2. This guy looks at the timestamp and says, hey, x has clearly got to be 11. Let me go ahead and write x is equal to 11 right back to our stale node. So that's read repair. Simple enough. Another thing that I want to talk about a little bit is version conflicts. So at least to my knowledge, or when I had looked it up before, I actually only thought that Cassandra was feasible with last write wins. And it's possible that it is. I actually have to look into this after I finish making this video. But the gist is, at least in the original Dynamo paper, you can have version conflicts because you can have version vectors, right? So we can have concurrent writes. So an example of a concurrent write is something like the following below, where basically 3 different clients in a replica or preference list of size 3, all write to 3 different coordinators, and then the coordinators basically have a brutal race condition where now all of a sudden all 3 nodes still achieve quorum, but at the same time now all disagree on what the values are. So you can think how this one might work, but basically this guy goes to this guy as the coordinator. He says, okay, I'm going to apply this locally, and then I'm also going to apply it over here, but then he gets overwritten by this guy, which is also coordinating, and then all of a sudden, finally, this guy gets overwritten by this guy over here. It's a real clusterfuck. I don't want to think about it too much because, frankly, it's just going to have to make me edit this video to explain it, but hopefully the diagram makes sense a little bit. If you think about it, if every single write is applied at t equals 1 to the coordinator and then applied at t equals 2 to the second node that they're writing to, then we have this race condition. So again, we can have version conflicts. And what does Dynamo actually allow us to do? Well, they've defined 2 terms in the paper that I hadn't seen before. Number 1 is something called syntactic reconciliation. What this really means is basically there are certain functions where you can merge these 2 writes in the database. almost like a CRDT, right? We look at the two version vectors, we say, okay, we have this data structure, we understand that these are concurrent writes, but we have some sort of way of automatically merging them for us, which is great. On the other hand, sometimes you can't automatically merge writes, and you need application-specific logic to do so. That's called semantic reconciliation, and Dynamo does allow both. Now, it is preferable to do the top one, because then you don't have to store all these siblings, but Dynamo does allow storing siblings, and then the application specifically can handle the semantic reconciliation, and then basically upload those back to DynamoDB and resolve the conflict. So interestingly, I found this to be a cool stat. They found that in reality, 99.94% of requests to their shopping cart service, which did allow conflicting writes, had just one version. So it really is very, very infrequent that you're going to have to store siblings. But at the same time, when you do want to be able to merge them intelligently. Okay, so another piece to talk about, again, which I've spoken about on this channel a little bit before, but hopefully this will be a bit more detailed, is something known as sloppy quorum or hinted handoff. So the issue with quorums, I guess, is that, if you do eventually have enough node failures, it's going to be really hard to achieve a quorum because you do still need to write to W places. And so as these nodes fail and as you have to read from R places, it becomes harder and harder to do that. So the whole kind of ethos behind Dynamo is that we always want to be able to accept writes and we always want to be able to accept reads. So the gist is, even if we can't achieve quorum, what can we actually do? Well, what Dynamo has chosen to do is basically say, okay, if I'm a node and I'm coordinating a write, and I find that one particular node won't respond to me, and I actually get so few responses that I can't achieve quorum, basically keep looking at nodes down the preference list or down the hash ring, continue to go clockwise around that ring, and then just send the write to the next possible node that will give me a response. So that's known as a sloppy quorum. The reason being that we're not achieving it over the nodes that are in our preference list, but we're just achieving it over any random node in Dynamo. Cool. The good thing to note is, of course, it is deterministic, right? We are still going to be using the same node every single time because we're basically just following the hash ring to figure out which node we're sending these hinted handoff writes to. So basically, these nodes are now going to receive this hinted data, and what they're going to do is they accept that it's temporary that they're storing this. They want to eventually give it back to the right nodes. And so what they'll do is put it in basically a separate database or a separate file locally, store it in a separate area so that they can easily transfer it out, and then eventually they'll keep heartbeating the node that is down that they want to come back up, and when it does, it'll send over the data. So of course, this is going to ruin some of our guarantees with quorums. It's possible now that we're more likely to get version vector conflicts as a result of this, but ultimately this does ensure proper availability, and we can always deal with siblings or version vector conflicts down the line. So yeah, another thing to note is, again, another way of ensuring that we get a lot of availability is dealing with the concept of having data center failures. So Dynamo always configures itself to do replication across these data centers. Nice. Okay, the next thing that we're going to be talking about a little bit is anti-entropy. So basically, the main idea here is that we're going to periodically sync up our replicas, right? We've got multiple different replicas in our preference list, and we don't want them to get too out of sync with one another if for whatever reason they have been. So the way that we do this is, we want some kind of methodology to quickly tell the difference between the data rows in one replica and another. And the way that we've discussed doing this in the past is using Merkle trees. So basically the concept of a Merkle tree is, you would go ahead and take the hash of a whole tree. And so what we can do here, I actually have a typo on my thing. Imagine this is some other hash. You basically take a hash of every single row in your table, and then you take two hashes combined, take a hash of them, and then you take those two hashes combined over here and take a hash of them. The reason for this is that I can look at these two Merkle trees, which are slightly different, and say, ooh, this hash is different than this hash, which means we have some rows that we want to synchronize between one another. Then I look at the two children and say, okay, this hash is the same as this guy, so we're totally good here. We don't have to keep looking down this side of the tree. However, these two hashes are different, which means they must have a different row between them, or at least one row that's different between them. So let's keep iterating down the tree. Oh, you know what? This guy is the same as this guy, so we don't have to worry about that. Ooh, you know what? These two are different. What's the actual underlying row associated with that particular hash? And then they can reconcile them based on the version vector or the timestamp or whatever it is that we're using. So I guess now that we've touched upon anti-entropy, we've really set the scene to talk deeply about Dynamo's problems with consistent hashing. So this is going to get pretty interesting. Basically, right now, let's imagine that we have n equals 3. So that means every single key on this ring is going to be stored in 3 replicas. And so basically, it means that A's primary node is over here, its second replica is over here on node 2, and the key range A's third replica is over here on node 3. Basically, on the left, every single key is stored on node 1, 2, and 3. The problem is, let's say that we want to go ahead and add a node. And so we add node 4 over here. So node 4 now basically has key range A1 on it. It's got key range C on it because, it's again a replica, so you just keep traversing clockwise. And it's also got key range B on it. It doesn't have key range A2. Now note that basically adding node 4 is going to remove a key range from every single one of our existing nodes, right? Node 1, node 2, and node 3 now actually don't have to store as much data. And so as a result, they have to actually recreate their Merkle trees for a piece of the data. So for example, let's look at node 1 over here. Note that node 1 is no longer storing the data for node B. And so as a result, it has to it has to remove their Merkle tree there. And now A2 and A1 are separate key sets, and so it has to make individual Merkle trees for A1 and A2. So that is going to take a good amount of time. It's an expensive operation. So we don't really want to do that. Additionally, keep in mind that when node 4 comes up, these existing nodes are going to have to send it some data. They have to send it part of the key range. And actually scanning the local database for what to send is what is going to be expensive, right? This guy over here, node 1, is going to say, okay, well, you know what? I have to look for all the keys in this range A1, and that scan is then going to go over to node 4. But that's expensive, and so we obviously want to avoid that if possible. So how does Dynamo go ahead and avoid that? Well, they do something pretty interesting, which is they use fixed size, predefined data partitions. So they'll actually pre-partition the whole key range on our consistent hashing circle into a bunch of small pieces. Right? We've basically pre-partitioned out our key space. And so now what we can do is, rather than having to basically split up an existing key range and make 2 new Merkle trees out of the individual pieces, we actually just keep a Merkle tree per partition. And so this way, now all of a sudden, we have all of these separate files, and they're going to hold the data of just one partition. Great. So now what this means is, let's say I have to go ahead and send, so previously this data right here was living on, this data over here was previously living on node 1 because node 1 is the third replica for it, but now it's going to live on node 4. So node 1 now can just say, instead of scanning for all these rows, every single one of these is its own individual file. It can take all of these pieces individually. It's not a scan because you're literally just going to the proper file path and then transferring the file itself over to node 4, which is great. That's super easy. Additionally, since all of these things are their own Merkle tree, rather than having to basically, take this combined key range over here, or rather, take the whole uninterrupted key range and basically, split it into 2 Merkle trees, we basically just delete the Merkle trees for each single one of these partitions, which is super duper easy. We can just go ahead and throw out the files for them. Cool. So now note that in addition to node 1 wanting to give data to node 4, basically node 2 and node 3 are also going to want to give certain partition data to node 4, because again, keep in mind that every single key is on 3 different replicas. So you can go around the hash ring and see that there's certain data that was stored on all of these nodes that node 4 is now going to take on. So when we do that, we might potentially be sending redundant data to node 4. It's possible that 2 of the same nodes are going to try and send the same thing. So basically, before actually sending all of that data to node 4, one quick optimization is every node will basically say, hey, node 4, do you already have this partition? And if so, I won't send it. So basically, yeah, the gist is that pre-creating our partitions is really great because you don't have to, previously over here, this whole range of A is 1 Merkle tree. And when A gets split in 2, now we have to basically kill that Merkle tree and recreate it into 2 pieces. And the problem is, it's not like we know exactly where our Merkle tree is getting split, because previously this guy number 4 is getting added to some random part of A. It could be added anywhere. And so there's no way for us to pre-partition our Merkle tree to easily get rid of it. That being said, when we actually use fixed size partitions, by keeping one Merkle tree per partition and never changing the actual ranges of each partition, then we can quickly send over partitions between nodes, and we can quickly delete Merkle trees on one node and not have to be recreating them all the time. That's a pretty fundamental concept, so hopefully it makes sense. Okay, another piece of this is going to actually be balancing load. So basically, like I mentioned, we're using fixed size partitions now, right? And so we want a lot of them. We want a bunch of really small ones that we can easily send them from node to balance them out. And then basically, even though we have all of these small partitions, we do still want a good amount of them on each node, but we want to keep the number of them relatively even on each node, or at least proportional to the hardware capabilities of each node. And Amazon found that when measuring performance, doing this rather than having a random number of partitions per node was actually the best way for them to balance out their load. They measured this by basically the mean node load over the max node load. That sounds sexual, but it's not. And the gist is, if you assign every single node the same number of fixed partitions, you can get a really nice load balance. Cool. One problem of this is, of course, basically that, now all of a sudden, if I have my hash ring here and a new node gets added to it, pretty much if we want to keep the number of partitions the same on every single node, now regardless of how many of these guys we have, they all have to send a little bit of data to it. And that is going to require some coordination, and it's going to impact every single one of our nodes, which is a downside, but ultimately it does keep load spread out more evenly in the long run. Cool. Another piece of this that I wanted to touch on is the actual gossip protocol aspect of it. So we're going to talk about sharing the ring now. Like I mentioned, every single node is communicating with every other node to express its idea of what lives where in terms of the keys and the partitions. So basically, nodes can be manually added or removed from the Dynamo cluster. This is going to be done and shared by some sort of gossip protocol, which is eventually consistent. And that's totally okay, right? Because we have all of these replication synchronization techniques between hinted handoff, between read repair, between anti-entropy. As long as everyone eventually agrees on what the configuration is, it's totally fine because we'll eventually sync up all of our replicas. Cool. So one problem that you might note is, let's say Dynamo starts out and we have 0 nodes, and then we add this node over here, we add this node over here. They both think, okay, well, I'm the only node in the Dynamo cluster. How are they going to know to gossip with one another? They can't, because their ring is just like them and them. They have no idea to communicate with one another. So what Dynamo will actually do is add something called seed nodes, where seed nodes is just like, okay, we've got Zookeeper over here. Zookeeper knows about this node in advance. And so if this guy joins, it can actually just go read to Zookeeper and say like, okay, well, give me a couple nodes to at least start with so I can start gossiping with others. So this guy will read from Zookeeper. It'll say, oh, wait a second. I see that there's another node over here. Now I can gossip with it. And then all of a sudden they realize that both one another are existing on the ring. Cool. So that avoids something known as logical partitioning. And then finally, one thing worth noting is that Dynamo nodes don't actually share their failure states with one another. They basically keep track of this information completely locally. If I am a node and I think that another node is down, causing me to do like a hinted handoff or something, even if I do a hinted handoff to another node, if the other node has a different view of the failures of other nodes in the cluster, it can pass the data off accordingly. That's totally fine. Okay, some random other information before I get to the conclusion of this video, which is finally coming, if you would believe it. So number one is basically Dynamo has a bunch of background tasks, right? We mentioned things like anti-entropy and things like passing off, your hinted data, stuff like that. And so what it'll do is it'll actually monitor the load on each node. So that'll be things like our disk latency, our lock contention, our request queue times. And then when that's particularly low, that's when it'll try and bias itself to run more of these background tasks. Number two is that Dynamo does allow basically writing into memory. So you would have this write back cache in memory, if we want to improve our performance a little bit, because some of the Amazon services do need better SLAs. And so what you can do is, you write into memory and then asynchronously on some other thread, write to disk on an interval. Now you may think to yourself, okay, well that's not very good for data durability. How does Amazon deal with that? Well, the gist is they do one thing called a durable write. So even though you only need to write to W nodes to achieve quorum, they'll randomly choose one node, because we're still going to try to write to N nodes. We're going to try and put it on all the replicas. So that way we will have one straggler, because one write has to go to disk. But as long as W is less than N, basically the one disk write isn't going to slow us down from actually achieving our quorum on the write. Cool. And then the last piece is that they support multiple storage engines, at least internally. So they use something called Berkeley DB, MySQL, and also that in-memory instance that I just touched upon. Okay, wow, so this was a long one, but I think I do have a few important takeaways, right? So I think when I read a paper like this, my biggest concern is less with the actual technical piece and more of the patterns and the actual software design philosophies that they used a little bit, and I think there were a few really good ones here. So first off, I just wanted to get the main motivation, why Dynamo? Why did we get rid of SQL? What was really failing them with that old relational database model? And I guess the gist was it was overkill, right? They only need primary key access. And basically, we don't need all of these ACID guarantees. We don't need strong consistency. We just always want to be able to write and read. It's okay if we're reading stale data. It's okay if we have to resolve conflicts down the line. If someone writes a piece of data, we don't want to lose it. If someone is going to our site, we want to give them as much information as we can, even if it's a little bit stale. Number 2 is node symmetry. So if you notice, in this entire design, everything is basically focused around every single node being equal. There's no special node that holds metadata or does any naming or anything like that. There's very little coordination or anything like that. There is the seed node thing, but I mean, Zookeeper is kind of an external system to this. I would marginally count that as breaking symmetry. But yeah, it's very impressive because a lot of these distributed systems do have this kind of single point of failure node, and Dynamo is completely decentralized, which is super, super cool. Number 3 is going to be data partitioning versus data placement. So what that means is basically, we can have our consistent hashing ring, we can break it into all of these little chunks beforehand, and then that's our partition, right? This is considered a partition. But when it actually comes to, which node does this thing live on, we don't break that down at a per partition basis. We can have multiple different partitions living on one node. And by doing kind of internal partitioning on a single node level, now all of a sudden we can send individual partitions to other nodes super quickly. We don't have to worry about, constantly breaking down and reconstructing our Merkle trees. Things become a lot more efficient. And then the last piece, which I think is really, really crucial for Dynamo success, especially within Amazon, according to the paper, is tunability. Right? You've got multiple different microservices, and they all want to do different things. And so being able to choose your number of replicas, your number of successful reads that you have to get for a read to be considered successful, and the number of successful writes that you have to be able to make for a client to see a write as successful is extremely important, right? This is basically tuning your performance and the needs per service. And so being able to do this made it useful across multiple different services, and I think that's really why it gained so much popularity. If it was always hard stuck to a 3-2-2 configuration or something, maybe this wouldn't work so well internally. And then another thing is you also have your choice of underlying data store, which again, if you really need good performance, you can opt for memory. If you want to get a little bit more durability of your data, you can just opt for writing to MySQL. And I think this is a really, really cool thing when thinking about building your own system, is thinking about the modularity of it. Anyways, guys, I really do hope you enjoyed this video. As always, I will try and answer questions about this in the comment section. Also, the paper is going to be linked. I'm really just covering stuff in the scope of the paper, and it's super dense, right? I understand this is still an almost an hour-long video, but considering it took me about double that to actually read the paper, I think this is a solid takeaway. So yeah, hope you all enjoyed the video. Enjoy your weekend, and I'll see you in the next one. Hopefully I can get some MapReduce going.